Well, thank you very much. I'm going to be talking about real-time audio on Android. So as Tobias said, I worked at Android Audio at Google for about 12 years. And I joined Google because I wanted to solve a problem. I wanted to be able to write Android apps because I like Java. And Android was sort of notorious for having very high latency. And sort of like 500, 600 milliseconds, for latency, which is very noticeable, big problem. And so I figured I'd go there, work on that for about 6 months, and then work on something else. And after 12 years, we made progress, which I'll be talking about. There's still work to be done. So it's turned out to be quite a big problem. While I was there, we developed AAudio and Oboe APIs, and I'll talk just very briefly about those and sort of how they affect latency and performance. So I'm not going to be giving any confidential information here, obviously, in case any lawyers are watching. But a lot of this stuff, what makes it easy is that Android and AAudio are all open source on AOSP. You can go in, you can look at the code, you can see how the stuff is implemented. Oboe is on GitHub and on the Play Store, or OboeTester is on the Play Store. The vendor docs and the CDD, which I'll be referring to, are all online. And the test tools that I'm using and referring to are on GitHub and on the Play Store. So these resources are available. You can experiment with them yourself. So real-time audio, defining as audio that changes quickly in response to user input or other information. So, excuse me, the applications that are involved here are games, musical instruments, even UI sounds, things that happen in response to a user. Hearing aids, hearing assistants, VR, voice over IP, these all require good low latency and real-time response. Things that are not affected are like streaming audio, listening to Spotify, listening to YouTube. Now, for most of that's probably one of the major use cases is streaming audio. But, excellent, got louder. But the real-time audio use cases are obviously important to people in this room who are involved in music and games. So there's two main issues in getting real-time audio. One is getting as few small buffers as possible. The latency is basically the sum of all the data that's sitting in all the buffers between your application and the speaker. So if you add up all those frames of buffers, that'll be your latency. And the other issue is reliable CPU performance. So when you have small buffers, you got to work very quickly to get those filled. So we'll be talking about both these issues. The good news is that if you have an app with a low CPU workload, it's fine. Android's now, the water's fine. Jump in. It's working great. Example, apps like a drum pad where the drum sounds not very CPU intensive. Drum pads like apps work great. So talking first about audio latency, I'm sure you all know what latency is, but just in looking at the contributors to latency, if you're using an audio processing application like, let's say, a distortion fuzzbox app on Android, you've got microphone, or actually probably a guitar adapter going through audio inputs. You've got audio input latency, the application latency, and then the audio output latency. If you're doing an on-screen keyboard, you've got the touch input latency, which is typically higher than the audio input latency. So the audio input latency is probably under 10 milliseconds. Touch input may be sort of 15 to 30 milliseconds. MIDI latency, if you plug in a USB MIDI keyboard into Android and you're playing, you're going to get very low latency because the input latency will be under a millisecond. So then you're just looking at the application and the audio output latency. One of the things that we measure latency with is the OboeTester app. So this app is available on the Play Store. The source code's on GitHub. And we use this all the time. It's primarily used as a debugging tool where people would call up and they say, I got this bug if I use mono with this usage, with this setting and this and that. Rather than write a program, we just dial in these settings and try to reproduce bugs. And also use it for measuring CPU performance, latency, all kinds of things. So the UI is something that would give a user experience designer a nightmare. I mean, it's like the horrible user interface, but engineers seem to like it because it's packed with information and lots of options. So in this case, you can change settings. You can see what's the effect of if I change the sample rate, how does that affect latency? If I change, other, buffer sizes and things like that. So we can measure latency for speaker to microphone latency, or USB round trip latency, or if you're lucky enough to have a 3.5 mil jack on your phone, you can plug in a little adapter and measure the latency with that device. So the same algorithm we use in CTS Verifier, which I'll talk about later. So this shows this is like an audio interface with patch cables connecting the output to the input. So we send out an output signal, loop it back in, measure the input signal, and test the latency. So I want to, what a lot of the manufacturers are using are these little USB dongles. So Google made a USB dongle, the white thing, and then the black thing is actually a hardware analog loopback, which is this circuit here. And those are, you can buy those online. You can search, you can find them on the Google website. You can build one. But one thing that was a big surprise for us, these adapters, we just assumed that they would all have this kind of 1 or 2 milliseconds that we were seeing on the Google adapter, but people were reporting that their devices had an extra 60 milliseconds more latency than we thought they would, and it turned out they're in the adapters. So if you're using some of these adapters and you're like maybe selling a game on a mobile platform and your users are plugging in one of these little USB adapters and putting on their headphones, they're going to be very sad because they'll get 40 to 60 milliseconds extra latency. We measured dozens of adapters, and we found that the ones from Moshi and Zoomi have 2 or 3 milliseconds latency, but most of them are really bad. So something to watch out for. This device is really nice because it has a loopback switch. So you just get this little, it's about a $90 audio interface, USB audio interface, and you just plug it in, flip the loopback switch, and you can do round-trip audio testing. So I just wanted, because there's a lot of DSP folks in the room, I just thought I'd run through the 4 techniques that we tried for measuring latency with varying success. So the first technique we used the Larsen effect, which is basically an echo. So if you send out a signal like hello, you get hello, 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 hello. Problem is if the gain isn't set correctly, it might be hello, or it might be hello, 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 and everything blows up. And so people are always trying to tune the gain, and you get these sort of sub-octave fake signals, and there are a lot of problems. So, and it didn't work with speaker microphone. So the next thing we do is we just played a sine burst, and then we would do a correlation between the input sine burst and the output sine burst, and we'd find, we got a very broad sort of correlation pattern. We'd often get these octave errors, and the sine waves would sometimes get blocked by very helpful software that was trying to prevent feedback, and sort of this feedback suppression. So that didn't work so well. Then we tried taking a random bit stream and using Manchester encoding, which is actually an encoding system used by Ethernet, like at the very lowest level on the wire. And it's just a way of encoding bits in a way that's self-clocking. So it either sort of, it either changes between twice per bit or once per bit. And that gave us a really, really sharp correlation peak, very unambiguous, beautiful correlation peak. But when we tried it on a tablet, the data path lengths from the 4 different speakers, you took this really high detailed, high frequency information in this signal, And they would all converge on the microphone, and it would just smeared out the data, and then the correlator couldn't recognize the data. So that didn't work on tablets. So we finally settled on this technique, which is basically little pulses of white noise, and they're kind of staggered so that they don't correlate, against each other. It's like there's only one position that'll really match. It's like a lock and key. So when you're doing the correlation, you get a strong signal. And we would do a first pass at like a low sample rate, just do an envelope filter over it, do a very coarse pass to get the rough idea where it is, and then we do a second pass with over a smaller range to get to the sample accurate latency measurements. So we'll diversion into a DSP land there. So as most of you know, sound travels 1 foot roughly per millisecond. That's 34 centimeters to folks more scientifically inclined. Like a 100 millisecond latency is like a sound happening, 109 feet away. So this was a report from 2021 where we measured the latency of the 20 most popular Android phones, and we found that in 2017, the average latency on those was 109 milliseconds, and by 2021 they were down to 39 milliseconds. And we'll talk about how they did that. But these are just 20 of the most popular phones, and there are probably around 3,000 SKUs for Android phones that come out every year. And so what's happening with the rest of them? Well, we've finally figured out a way to get that information by requiring that the manufacturers measure it and then send us the information. So what we did, we have this thing called the Android CDD, which is a compatibility definition. And we required that when they turn on the low latency mode, it had to be under 800 milliseconds, which is ridiculous. It's like that's like horrible, right? But we're confident that everyone would be under that, and if they weren't, they probably shouldn't be shipping. But what it did is it forced the manufacturers to get set up to measure latency, do the latency measurements, and then report to us. So then we had latency figures on all 3,000 Android phones, and we could look at the distributions. I can't give you the numbers, but obviously most of them were skewed, kind of in the comfortable range. But then there was a long tail on this. Luckily, the long tail devices were mostly things like $50 kid tablets or something, with sort of more toy tablets. So what we did is each year we'd get the information, and then we just drop the latency requirement again, and it's just kind of squeezing the manufacturers. So again, most of them are down, under 100 milliseconds, even under 50 milliseconds. But because they had to keep measuring it, and they knew that the ceiling is dropping on them, they did a lot of work to measure or to reduce their round trip latency. And now we're in a pretty good place for Android. The majority of Android devices, the ones you would care about in terms of the people who are going to be, downloading musical apps and doing a lot of apps, are now under 30 milliseconds round trip, and some of them are below 10 milliseconds, which is actually below, the iPhone latencies. And one reason for that is because they don't have fancy DSPs. They maybe just have a DMA, and so they just take the data and DMA it right to the speaker, so they get very low latency. So this is good. So from a latency standpoint, if you're playing pulses of white noise or a sine wave, it's great. You can get really low latency. But the other part of that is keeping the buffers full. So like I say, it's solved for interactive apps. This Drum Thumper app is a good application. It's on the Play Store, and you're tapping on the screen. Most of the latency you're going to be hearing is actually the touch input latency, which is determined by the scan rate on the screen. But it's quite playable. I've had world-class percussionists sort of play it and go like, oh, I could play this on stage. I mean, it's playable. So the way that we got to this low latency point is with AAudio API, which was a new API that was added just for these kind of high performance applications. When you're streaming audio, you're generally going through the older part of the Android framework, but AAudio is a native API designed for high performance. And so when you create an exclusive stream in AAudio, you're creating a buffer in shared memory, and your application can call the API, and in the same thread, it'll write the data into the buffer. And that buffer is shared with the hardware, and then the hardware will read directly from that buffer. So you're writing to a buffer, and the DSP is reading it. You can't get any less than that. There's not multiple stages of pipelining and big buffers, and you can get that buffer to be quite small. So this is, this buffer, typically we run like 4 milliseconds of data in that buffer. The extra latency comes from the buffers in the DSP that are doing things like speaker protection or, buffering on the way to the USB or, some of their internal processing. So so the system is capable generally of getting low latency, but that doesn't mean your app will have low latency. There are certain things that you need to do. If you use the Java APIs, you can request low latency and you'll get decent low latency, like maybe 30 to 70 milliseconds output. But if you really want low latency, you need to use native code, C++, and use Oboe, which has it's a C++ wrapper for AAudio and OpenSLES. And it's got things like a quirks manager, and it's got various things that will make it easier for you to write your applications. You need to actually request low latency. And you can request the exclusive mode where your app is the only app that's writing into this shared memory buffer. And so you can usually get that unless there's a lot of other stuff going on. And so that'll save you a bit there. Also, it's best to just let AAudio tell you what the sample rate is. It'll almost always be 48,000 hertz. On some devices, it might be 44,100. If you specify a sample rate, and if you let the operating system do the sample rate conversion, often you could add maybe 100 or 200 milliseconds of latency because of some architectural issues that cause you to go through a certain path. Oboe has its own sample rate converter. So if your source material is, some other sample rate, 32,000, whatever, because it's coming from voice over IP. If you use the Oboe sample rate converter, which is on GitHub, open source, by the way, it's a nice sync-based sample rate converter, and it will only add, like 2 or 3 milliseconds additional just to get through the FIR. Also, if you set the audio usage to audio usage game, then you'll get a good path through the system, and also it can help if your poor user is using Bluetooth, which they're going to have hundreds of milliseconds, but it may by using audio usage game, it may use a special codec, and they may get them from 500 milliseconds down to 250 milliseconds. If your users care about latency, tell them don't use Bluetooth, use a USB, like one of the adapters that we talked about. You want to use data callbacks. You'll get a high priority thread that will avoid preemption and avoid some of the CPU problems. Sometimes that's not possible. Often if you're like doing network streaming, then you end up doing blocking writes, and that's okay. The other thing is you want to tune your buffer size to probably a double buffer. And I want to mention some terminology here on Android that I find useful in talking about buffers. So the first term is the burst, and that's sort of the amount of data that the DSP or the DMA will process at a time. That's often 1 or 2 milliseconds. And then there's the buffer capacity, which is the amount of memory that's allocated for the buffer. So there may be 16 or 32 bursts in there. Now you don't if you fill up that entire buffer with data, you're going to get 64 milliseconds of latency. So what you want to do is not fill it up. So you can set what's called in the API the buffer size, and that's the kind of the effective size. So it's kind of like if you're driving around in a gas tank and you can fit 14 gallons in your gas tank, it doesn't mean you have to have 14 gallons. You can only fill it up to 2 gallons and then let it run down. And so you never got that much gas in your tank. And you can do that with this buffer. You say, when I go to write, I want to just not go above 4 milliseconds worth of data, 2 bursts. And then it'll just wait until it'll call me back as soon as it drops back down to a single burst. So by doing this, you can keep your latency down. And you can also dynamically tune this. So when you're running in your app, you can periodically check. You can say, did I have an underrun? Did my buffer run dry, which means I'm going to get a big click. And in that case, it may mean that on this particular device, your buffer's too small. So you can check you can go get X run count, and if it's increased, then you just set the buffer size in frames to be 3 bursts or 4 bursts, and just keep doing that until you find a level where you're not glitching anymore. And then you could save that on the device and then say, okay, on this device, I need to have 4 bursts, but on this device, I can use 2 bursts. So hopefully you don't have to go to 32 bursts. So we can get small buffers. That's a solved problem, really. But once we solve that problem and we realize that people are still complaining and they're saying, well, sure, I can get down to 4 milliseconds, but it's glitching constantly, And I say, well, I run my test app with a sine wave and it's not glitching. But when you start running, complex voices like granular synthesis, or doing some spectral processing, some heavier CPU load, you can start getting glitches. And the problem is that with these very small buffers, they can run dry. And if you're not there delivering data every 2 milliseconds, then you've got problems. So this is now the focus of the work that we're doing. Unfortunately, the CPU performance is not handled by the Android audio team. So the people that care about it don't directly have the power to fix it. So our job is basically convincing all the people who control the kernels. There's the Pixel team, the Samsung teams, the Samsung Mobile, Samsung Exynos, the MediaTek teams, Unisoc, all so going to Korea, going to China, showing them slides, showing them demos, saying there's problems, there's issues in the kernel. How can we work together to fix them? So we've been writing tests to demonstrate these issues, trying to categorize them. We're adding, valid conformance tests, validation tests, because I think this is the area where the problems still remain. So good news is that the CPUs are very powerful. So we, defining a voice, we have an app called SynthMark, which is a synthesizer benchmark. And one voice, a SynthMark voice, is basically a virtual analog mini Moog. So we got 2 oscillators, resonant biquad filter, oscillators are band limited, an LFO, a couple ADSRs, something like that. So a little classic mini Moog voice. And on my phone, I can play I can get over 700 voices I can generate on that phone. So that's a lot. Probably more than you would need musically. But like I say, if your voices are much more complicated, then there's fewer voices. The problem is the energy-aware CPU scheduler. So there's another team in Android, and so there's the audio team, which our job is to try to deliver high-performance audio, and there's another team which is trying to make the battery last all day long, and they are working very closely with the kernel team to make sure that they fight back against every additional use of the battery because they really want that thing to be, still have battery life at the end of the day, which it's a good thing. But these two goals are in conflict with each other, or often in conflict. And so this causes 2 problems. So they're trying to get as little CPU usage as possible, and we're trying to like use the CPU appropriately for real-time audio. And this results in two main problems. One is that the CPU responds too slowly when your workload changes. And I'll go into detail on both these things. And the second problem involves core migration. And I'll just say that there's some behaviors there that are not optimal. So the CPU scheduler is responsible for many things. One of them is determining what the frequency is they should run the CPU at. So the bottom frequency is maybe like 300 megahertz, the top frequency is maybe 2.5 gigahertz. So, there's quite a range there. And as they go up in frequency, as the frequency goes up, the period goes down, and you've got less time for the signals to propagate through all the digital logic. And so you want those gates to switch faster. And so after you get to a certain frequency, you've got to bump up the voltage, which will make the gates switch faster. When you increase the voltage, that will increase the power, which drains the battery. So they try not to do that. A funny thing about this is that on a given level, when you're doing real-time audio, at least, the power consumption at the lower frequency is pretty much the same as the power consumption at the high frequency. So if you're at this level, you might as well be here, because if you're here, you're running slow, but you're not going to use any less battery. And the reason is the new processors have very little leakage. So as you run faster, they just, there's current that flows every time they switch the gates. So it's really just a question of how much computation is there going on. So the power is really proportional to the computation and the voltage. So as you increase the frequency at a certain voltage, what happens is that you do the same computation, but you do it in less time. So you race to idle, you use that power, then you're quiet, and then you race, finish, and you're quiet, versus like running at lower power for a longer time. And so it's like the same power. So I'm trying to convince manufacturers to, if they're at a certain voltage, just go here. Don't bother with these levels, because you're not saving any, it doesn't save any power when you do that. So if there are any kernel scheduler writers out there, please try that. So what is this slow response to a changing workload? So if you think of your current workload in a synthesizer, maybe you've got one voice, dum, 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 and then suddenly you go from one voice to 10, right? If this red line is the maximum workload that you can do based on the frequency, in this case, you're fine. You're like half your, load. And, if you double it, you're going to be just above the level that you can do in real time. If you go 10x, you're way above the amount of workload that you can handle at that frequency. So what happens is CPU goes to 100% utilization, and the scheduler, it takes a while, and the scheduler goes, oh, they're running at 100% utilization. I don't know how much they really need, but I'll just bump them up and see what happens. And it bumps up and it goes, they're still running at 100% CPU utilization. I'll just bump them up and see what happens. Still running at 100%. Okay, we'll bump them up again, and just keep doing this, and eventually we get to a point where we're like 80%. They say, okay, we're good. This can take 100 milliseconds, and if you have a 4 millisecond buffer, then you've run out, around here. You're glitching by around here, and so you get significant glitches. So one of the things I'm trying to convince the kernel folks to do is when they see this situation, just go to the maximum. Very briefly, get above it, look down and see, okay, I'm at the max frequency, I'm running at 60%. I'll drop to here, and then I'll be okay. And you can do that really quick. You're going to want to get to this point anyway. Rather than wasting 100 milliseconds and making noise, just burn a little bit more power. We go to the right place, and if you do this, you can actually eliminate the glitches. So that's something we're working on. There's a tool called Perfetto, which it's free on Android. You go to perfetto.dev, and it lets you see all this stuff in action. And it's a very, very, very handy tool if you're writing for Android and you're trying to deal with real time. You can see, you can put in your own traces, your own waveforms, and you can see exactly what's happening, down to the microsecond level, and really analyze the timing and the interaction between your cores and so on. And so you go into ADB, log in, go into the shell, or just issue an ADB shell for Fedo, this command, and you'll get this trace. It'll get written to this file on the Android, and then you can pull it down and look at it. So then you open it, you run this website, open the trace file, you load it in, and then look for the traces for the COM, Mobile, or OboeTester, and you'll get something like this. This is a detail. It's actually bigger. So in this detail, what we're seeing, the top line is the AAudio thread that's running the callback in your CPU. So you'll see we're ticking along just fine. And then all of a sudden in OboeTester, we go from 1 voice to 70 voices. So boom, it saturates. We're saturating the CPU. AA ready is the data line, the amount of data in the buffer. You can see it starts dropping. When it goes negative, we're glitching at that point. So we're glitching for this whole period. This is about 100 milliseconds. You can see it, these, I think, I'm not sure where they were, but this might have been these orange lines here, and then maybe here. But anyway, you'll see this task going solid, which is a sign that it's it's saturating on the CPU. It's still running on a little CPU, and then it migrates over here. If you click on these, it'll tell you what task it is. Then it migrates here. Then it migrates over to these medium cores, CPU 5 and 6, and then we start. You can see it's caught up now. It's just running, at like 40% duty cycle. And then you see the data buffer filling back up, and then we're done glitching. So like I say, it take 100 milliseconds. So that's something trying to avoid. You can see this with the OboeTester app, which is a really fun little app. So in OboeTester, there's a bunch more settings on this. There's a bunch of settings. But what this will do, it'll jump between 1 voice and 70 voices. And when you do that, when you see this thing jump up there, the blue line's the workload, the number of voices. The green line is the CPU utilization. And you'll notice that when the workload rises, it spikes. And it turns red, which means you're getting underruns. And when that happens, you'll hear it. So if you, I'll turn this on, and yeah. So the first one, so you can hear this. So what I'm doing is I'm generating 70 voices, but then I'm also generating a sine wave, because the sine wave you can hear the glitches. If I listen to the synthesizer, so now I go to 70, and you can hear it crackling. But when you listen to the sine wave, you really, really hear it. Okay, so most people run demos to show how great their products are, but I run demos to show where we suck. Actually, I don't work for Google anymore, so they suck. No, it's getting much better. What's happening here, and so you can see the spike here. You can also see what cores are being run and the current CPU utilization. So you can get a lot of information, and you can really hear it. And if you try this on different phones, you get very, very different results. Some phones have no problems, and often it's the very inexpensive phones. And it's because they don't have very sophisticated schedulers, and so they don't have a very powerful energy-aware scheduler. They just run kind of hot all the time. Maybe they just put a bigger battery in there. They don't have enough engineering to really tune it so that they're driving the frequencies down. And so they just kind of work. So ironically, sometimes the cheap phones are better for real-time audio. Now, something you can do here, you notice there's a checkbox up there, ADPF. If you hit ADPF, notice it's not going red anymore. So the good news is there are things in the system that can help, and ADPF will give a boost on some systems. It's vendor specific, but there's still a little spike, but it's not enough to cause an underrun. And so I'll show you how you can enable ADPF in a couple slides. So that's one thing you can experiment with. The other thing you can experiment with, and I recommend this really just for doing diagnostics and trying to figure out what the problem is. The second problem I mentioned was the core migration problems. And I want to clock back up there. Okay. So after the initial spike, there can also be problems when there's core migration. And two problems that can happen there. One, the scheduler might move you to a core that is just ridiculous. Like if you're kind of, running kind of hot on a medium core, you're probably not going to be able to run on a little core, particularly because when it does core migration, it'll get rid of all the statistics for the big core, for the bigger core, because it figures, well, that's not valid anymore, on the little core. So it drops all the statistics, drops you down to 300 megahertz on a little core, says, here, try this for a while. And so you can see every time it does a core migration, we're getting a glitch. And now also notice this is at 50 voices. If I run with 70 voices, it glitches occasionally. If I bring it down to 50 voices, it's much worse. And it's just, the nature of the thing that maybe at this level, it does more core migration. So, your application's changing, the CPU frequency is changing, you're migrating between cores, you have other threads that are intervening. There's so many moving parts. The behavior of the system is very complex. So it's almost like studying biology or something where, you're just sort of poking at it and see what happens. One way to tell if you're getting core migration problems is to set the CPU affinity. So over here, we set the CPU affinity to number 2, which is a little core. And so you see everything's running on CPU number 2, and it's just glitching all the time. So that's not good. But if we set it over here on 5, we can see where, it's running strong enough, we're not getting the spike, and we're also, we're not getting the glitches here. So those glitches were related to core migration. So when it drops down to this core and comes back, we get those glitches. So this is a diagnostic tool that you can use to figure out, why things are glitching on a particular phone. This kind of stuff is also very handy for showing to the managers and say like, here, listen, listen to what this sounds like. And it's, and it's like, oh, okay, that's like bad. It looks bad and you can hear it bad. And it's easier. This was really written to convince, the manufacturers and kernel folks that like, hey, there's a problem that needs to be solved. So you can see this happening in Perfetto again. So here we are running on CPU number 4, really fine. It's about, the frequency, I'm not sure what that frequency was, but we're running fine on CPU 4, which was a medium size core. And then the scheduler just says, try out core 0. I think you'll like it. And it doesn't. It just, and then you see it going down, and it just sits there for a while and it says, okay, never mind, we'll move you back here to CPU 6, then back here, and then you're sort of fine for no particular reason. So, so these core migrations are a problem. So the kernel folks are working on this. I'm hoping to see some progress soon. So we had a checklist for things to do in for you. No, I think I skipped over some of that stuff in that slide. But for a checklist for good CPU performance is to obviously avoid any kind of blocking operations in your callback. Don't allocate memory. Don't read network sockets in the callback. Use the dynamic buffer size. And a lot of these problems, if you increase your latency by adding 10 or 12 milliseconds, that might be enough, and so you go from 15 milliseconds of output latency to 25 milliseconds. It's still usable, for most apps, and you may eliminate all the glitching. So that's like the simplest thing, to do. Obviously optimize, using -O fast or using auto vectorization or directly like using SIMD, turning on ADPF, which we'll look at. The CPU affinity, I think, is only as a last resort. If you do that, then you interfere with the scheduler, and maybe some other task is also chosen that same core, and you're both fighting over one core. And it prevents the CPU scheduler from working properly when it does. And then also adapting your polyphony levels dynamically. So ADPF in Oboe, there actually the last time I looked, there was no native NDK for ADPF. You can call it from Java, but there was no way to call it just directly. So we used DLSim to do soft links into the NDK so that you could make these calls. They're available. It's not like you're not violating anything to do this. But Oboe makes it simpler by having this ADPF wrapper. So you just open it and you give it what your target duration is. So if your target deadline is every 2 milliseconds, you say, I want to run every 2 milliseconds. And then when you begin your callback, you say on begin callback. And then at the very end, you go on end callback, and there's a scaler, which you don't have to worry about. So what ADPF will do, it'll measure what your actual callback time is. And if your target is 2 milliseconds and your callback time actual time is 1 millisecond, then you're fine. It won't do anything. Suddenly, if you go, hey, I did a callback and it took me 3 milliseconds to do what I should be doing at 2 milliseconds, then ADPF will say, okay, we've got a problem, and it'll boost the CPU and try to jack that up. And you can see that it really did make a difference. On more and more Android devices, calling ADPF will really help. On some it may not help, but there's no harm in calling it. In newer APIs, another thing you can do is in your callback, like usually the first thing you have in like a MIDI callback is you read your MIDI input and you figure out what notes you want to turn on. So you turn on a bunch of notes. Then okay, I just went from 1 note to 10 notes or 10 notes to 100 notes. So I know that, based on the statistics that I've been gathering from my previous duration, I know that I'm not going to make it. I know now that I'm going to underflow. So rather than underflow, miss my deadline, and then have the scheduler respond or have ADPF respond, I'll just tell it now. It's like, hey, I'll tell you right now, I'm going to miss my deadline. And you can report your duration. It says report actual duration, but you're really reporting your predicted duration. It said like, hey, if I continue at this current frequency, it's going to take me 5 milliseconds to do this workload. And then ADPF has this advanced warning, and it can respond much more quickly. And this will help ADPF, do the right thing more quickly. In API 36, there's a new ADPF call, notify workload increase. And you can tell it whether you're going to be using more CPU or more GPU. And it's just like, hey, we've had a bump, and it'll just kind of panic and jack the processor up and kind of do what we were hoping it would do. So this there's a doc for this on the wiki on GitHub. So on GitHub, Google Oboe wiki, and you just search for ADPF or the dynamic frequent buffer tuning. You can find a lot of good stuff on there. We used to recommend running a steady load, which would avoid this kind of slow ramp. And we tell people, if you think your maximum number of voices is 64 voices, just always calculate 64 voices. And then if you only use 2 of them, just throw away the other 62. And that way, you know, we don't have to worry about this slow response time in the scheduler. The problem with that is if you're only running 2 voices, you're not going to have a problem. As long as you're just running 2, 3, 4 voices. But if you're doing the steady load and you're running this max thing, then when you have a core migration, you're going to get whacked. And it's going to, you get a lot more glitching just because you're running with heavy load and you'll miss your deadlines because it's running all these voices that you don't really need. So we don't recommend the steady load anymore. Also, the CPU frequency can just drop sometimes. Without even migrating cores, it'll sometimes just drop. And if you're doing more calculation than you need, that'll bite you. Another thing you can do is monitor the CPU utilization, and then just adjust your polyphony. So most synthesizers have a kind of voice stealing algorithm that will steal voices that are almost inaudible, free up the CPU resources. So you can kind of adjust your polyphony and then save that in your, excuse me, as in sort of an on-device preference. As the last resort, you could benchmark the CPUs and then pick a medium core. But like I say, that can cause problems. Another issue for real-time performance, something that's rather tricky, is dealing with full duplex streams. So something that we recommend, if you are running a full duplex stream, let's say like a guitar effects processor, we recommend running your input very low and your output kind of full. And then if you get preempted, they'll sort of move like this and then snap back. If they're both full, then like your input will overflow, or if they're both low, your output will underflow as soon as you get preempted. So if you kind of arrange them like this, then you're more immune to preemption. So we have a class that will handle that. And then it'll just give you a call back when all the data is available. So Android, we say it supports real-time audio. The ADPF is working. There are ways to work around a couple of these core migration things. So it's ready. You can port your iOS apps to Android and they'll work. And you'll have access to a 3 billion user market of Android phones, 3 billion plus users. So yeah, any questions?